first, if I were to toss 3 coins in a row, I have 2 possibilities for each coin, right? And these possibilities are all independent of each other because the coin doesn't remember what it was tossed, what it came up as last time. So I'm going to take a look at that probability tree for the coins again. So if I toss a coin, right, there are 2 possible outcomes I can have. I can either have heads or I can have tails. That's my first coin toss, right? So if I get heads, the next coin toss I have can have 2 possibilities, heads and tails. If I had tossed the coin and came up tails, the second coin could come up heads or it could come up tails. Similarly, now if I toss it a third time, if it had come up heads and then heads again, well now this time it could come up heads again or it could come up tails. If it had come up tails that time, it could come up heads or it could come up tails. Similarly again, heads, tails, and heads, tails. So these 8 outcomes, right? All these 8 outcomes that I have are kind of a track of all the different possibilities, all the different outcomes I could have had. And they're each equally likely, right? Because it all depends on which way the coin happens to toss each time. And the probability of each is equal to 0.5. Just happens that in this particular example, the p-value, the probability of getting that particular outcome, say heads or tails, is 0.5, right? So let's see, heads, 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 heads. This probability is 0.5, this probability is 0.5, this probability is 0.5. So the probability of getting 3 heads, 0.5 times 0.5 times 0.5, is 0.125, right? 1/8. Everybody okay with that? Right? Probability of getting 2 heads and 1 tail is 0.125. Probability of getting a head, a tail, and then a head in that order is 0.125 and 125. So they're all the same probability. Well, each one of these outcomes has the same probability as it happens. What do I got? I got 6, 7, 8. How many ways can I get heads? All 3 heads. There's only 1, right? So my probability if I toss 3 coins in a row of getting heads is going to be 1 out of 8, right? 1/2 times 1/2 times 1/2, or 0.125. How many different ways do I have of getting all 3 tails? Same deal, right? 0.125. That's easy. We use the multiplication rule because they're independent, and that's what would happen if we wanted to look at them occurring one after the other. Okay, well, how about what's the probability of getting, how many different ways, and what's the probability of getting 2 heads here? Well, let's see, which one of these outcomes would give us 2 heads? Heads, heads, tails. So this would give us 2 heads. Heads, tails, heads, tails, heads. This would give us 2 heads. This one doesn't. Let's see, go this way, okay? Tails, heads, heads. This would give us 2 heads. Tails, heads, tails. This wouldn't give us 2 heads. Tails, tails, tails wouldn't give us 2 heads. So there are 3 ways, 3 possible outcomes that would give us 2 heads, right? So what does that add up to? 0.375. So what do you think these other 3 possibilities are? What's left? 1 head, right? Or 2 tails, whichever way you want to look at it. That's going to be 0.375 also. And what are these? Since these are all the different possibilities I could have, what are the probabilities going to add up to? 1. There you go. Do I need to stop here? If I want to get done tonight, I need to stop here. But I mean, in reality, I could just go on and toss more coins and toss more coins, and so on and so forth, and look at this. Look at this even deeper. What would happen if I had 4 possible outcomes? 5. If I toss 4 coins or 5 coins, or 50 coins or 100 coins, right? So this is probability I would get 2 out of 3 coins. Easy to see, easy to calculate. If I asked you, what's the probability that I would get? Let's say 10 coins that are all heads. Well, it's going to be 0.5 times 0.5 times 0.5 times 0.5 times 0.5, right? Because there's only going to be 1 path for that, and all those probabilities are going to be multiplied. It's going to be 1/2 to the 10th power, okay? So if I ask you, what's the probability if I toss 10 coins, what's the probability I would get 4 heads? But that gets complicated, right? Because there's many ways I could get four heads. Could be heads, tails, heads, tails, heads, tails, tails, tails. Could be so on and so forth. Many different possible ways for that to uh, uh, appear. Okay. The only problem is that very frequently those are the outcomes that we're most interested in. What's the probability that I'll get that I'll lose money, that I'll get fewer than five heads if I'm betting heads or something like that. Okay, so those are sometimes really the probabilities I want to chase, and they're not quite as simple as looking at the same outcome all the time. So I'm going to take a look at this from another perspective. Just so you know, let's say that if instead this was a test, and the probability of getting the answers right, instead of heads that we're going to talk right, is only 0.2, right? It's a multiple choice test with 5 questions. The probability of getting correct answer would be 0.2. Well, then the probability of getting all right answers, if you were just guessing, would be 0.2 times 0.2 times 0.2. But similarly, probability of getting it wrong would be 0.8, right? Probability of getting all 3 wrong is 0.8 times 0.8 times 0.8. And then I could use this tree to also calculate all the different permutations of 3 right, 2 right out of 3, 1 right out of 3, and so on, right? Well, I'm going to take this tree and I'm going to tilt it sideways. Let me see if I can't do that here. I'm going to go to the next page here, I think. No, I'll stick on this page. I don't want to play with that formula yet. I'm going to tilt this tree sideways. I'm going to say to myself, well, let's see. If I look at this first probability, right, and my heads or my tails, and from that one, heads or tails, heads or tails, and from that one, heads or tails, so on and so forth. Instead of looking at it as coins, let's say that, anybody know what a pachinko machine is? Got any idea? It's like a Japanese pinball machine. It's got a whole bunch of pins in it. The ball, instead of like hitting bells and bouncing around, there's pins, and it can go like down different paths and stuff like that. But it's got many pins in it. I'm going to set up kind of a pachinko machine where there's a pin at each one of these junctures, right? So if I drop a marble down here, straight down onto this pin, assuming it doesn't get stuck on top of the pin, like when a ball gets stuck on the rim or something like that in basketball, assuming that doesn't happen, which way is it going to go, left or right? Could go either way, right? So it's kind of like my coin, 50-50 chance of going to the left or to the right. Well, what do you think if I go down here? What's the most, if I drop, let's say that this goes down, there are 20 layers here, 20 different paths that it could take down here, right? Finally, at the end, we got 20 pins across, right? So if it's 50-50, and each time that it hits one of these pins, it can go, it's just as likely it could go left as right, then logically you would think that we would get, on the most common outcome would be half the time it would go left, half the time it would go right. So if I hit 20 pins, how many would I expect to be left turns? Right, just like before, 10, right? We'd expect 10 left turns, 10 right turns. So the most common outcome that we would expect to see is the balls in the middle here, right? What would be the least common outcome we would likely see? Is the ball making all left turns, or all right turns and ending up going all the way to the left or all the way to the right? Well, believe it or not, there is a guy that actually invented a machine like that to demonstrate this exact thing. It's called a Galton machine. Okay, let me open this up. Let me get this out of my way here. Okay, hopefully you guys online can see this as well. Okay, so let's see this machine. It's old film. Okay, so there it is. Here's the Galton machine. What's going to happen here? Take a look at these balls dropping down. Let me get this off of here so you can see it. See them coming down? Kind of hard to see them here. You can kind of see them over there. What do you think is going to happen at the bottom of this thing? See, as we pan down and see what happens here. They are piling up in different columns at the bottom. It's kind of a normal distribution, eh? Hopefully, I'll post this on Blackboard so you can actually play it for yourself, get a smoother version of it. Right? So pretty interesting. And see, these kids in the back are waiting for these all to pile up so that it'll flush at the end of it and make a lot of noise. But that's what they were doing there. This, by the way, is at the New York Hall of Science in Queens, if you're interested. And have a lot of interesting math and probability demos and stuff. Okay, so that's the most likely outcome that we would be likely to see. So let's take a look at how you might summarize that in terms of a formula. So this interesting formula, which you just worked out a moment ago, represents all of the possible permutations, all the possible different outcomes and the probabilities of them. So we can actually substitute in. What do we have here? We have n, which is a number of trials, number of balls that we drop, for instance. We have x, which is the number of successes. And we have p, which is the probability of a success. Probability has to be the same for every trial. In other words, we can't have a coin, we can't flip one coin, has a probability of 50%, second coin, probability of 40%, and so on and so forth. It's got to be a fair coin, let's say. So if we were to calculate, if I repeated the problem I just had before of what's the probability that I'd get exactly 2 heads if I flipped a coin 3 times, right? Let's use the formula instead of what we did before with the probability tree and see if we got the same answer. So that's going to be equal to n factorial, right? What's n factorial? N is the number of trials, right? Right, 3 times 2 times 1, right? Okay, what's x factorial? 2 times 1, right? Times n minus 1 factorial, that n minus x factorial, which is 3 minus 2, which is just 1, times the probability of success, which was, I'm sorry, I wrote that. Let me undo that. Let me undo it. No, it won't let me undo it. I'll just go do that. Times 0.5, which is the probability of success on any trial, right, to the x power. What was x again? Number of successes? 2, right? Right, 2 heads. Times 1 minus p, which is 1 minus 0.5, which is 0.5, right? Times n minus x, n minus that's 3 minus 1 is 2, is 1, right? So that's to the first power, which is just itself. So let's resolve this. First of all, 2 times 1, 2 times 1. So we got 3 times 0.5 squared, which is 0.25, times 0.5 to the first power is 0.5. So what do we have here? We got 3 times 1.25, which is 0.375, right? Same outcome we got before. So this formula represents our calculation that we could do to any power that we want. As Levi said, we could say, what's the probability of getting 37 heads out of 50 flips? For instance, we could actually use this formula, except it's going to be kind of cumbersome once we start working with factorials that are enormous like this. So instead of doing that, we're going to want to find a better way, right? We're going to find some other mechanism for doing that. Okay, so let me skip this page. Okay, so Excel has a mechanism for doing that for us. So I'm going to demonstrate this in Excel. Okay, let me check online, see how those guys are doing. They're not complaining, so things are good. Okay, I'll get that back up again. I'll blow this up. Okay, I have a kind of an image of what this is going to look like in the background there. But first, I want to give you a solid example of this. There's a function in Excel called binom dist. You're going to type it in, binom. I could use .dist. I could also just type in dist and hit parentheses. When I hit parentheses, you can't see it that well because it's in very tiny letters and it won't let me blow. Well, maybe it will let me blow it up. No, it won't let me blow it up, unfortunately. Okay, you can see that it's waiting for me to give it 4 pieces of information. Number underscore s, that's the number of successes. By the way, I summarized that in here. The number of successes, the number of trials, the probability for success in each trial, and it's finally asking me to give it something called true or false, a logical operator called true or false. And we're going to talk about that in a second. Okay, so let's say, for instance, I'm going to hit escape here. Let's make up a situation. Let's say that the prevalence of diabetes in a population is 10%, and I randomly select 10 people from that population. What's the probability that exactly 3 out of 10 are diabetic? Well, I could use the probability tree to solve that. I could use that equation to solve that, but I can also use Excel to solve that. So if I say 3 out of 10, so what's the number of trials there? 3 out of 10. Number of trials is 10, right? What's the number of successes? 3. Probability has to be the same for each individual. And what is the probability of each individual being diabetic? 10%, right? That's the prevalence. Okay, so let's give it a try. Equals binomial dist, right? Parentheses. Number of successes is 3, comma, trials is 10, comma, probability is 0.1, comma, and cumulative. I'm going to say false for that for now. Don't worry about it. We'll get to that in a second. And the probability is about 6% that might occur. Well, that's a lot handier than doing it the other way, right? Okay, so I'm going to do that. I'm going to do this a couple of times. I'm going to take another look at this. What do you think is the most likely outcome for the number of people that are diabetic in that population if I select 10 people randomly? 1, right? Right. So 10% of the population is diabetic. Pick 10 people, expect 1. So let's do that for 1. This is the number of successes. So I'm going to calculate that for this number of successes. Equals binomial dist. If you got your own computers, you can go ahead and do this also. Binomial dist. Parentheses. How many successes? Let's see. 1 success. I'm going to actually, instead of writing in 1, I'm going to click on the 1 here. It's the same thing. Comma, trials is 10. Not going to change. Comma, probability is 0.1. Comma, and cumulative, again, I'm going to write false. Close parentheses. This presumably is the most likely outcome. Okay, and it's about 38% of the time we'll get 1 person out of 10 if we select 10 people randomly. What do you think are the next 2 most likely outcomes? Well, just a little bit below that, a little bit above that. We wouldn't expect the next most likely outcome to be 9 out of 10 if it's only 10% prevalence. We would expect the next most likely would be either 0 or 1. So I'm going to do the same calculation for 0 and for 1, for 2 rather. Okay, so equals binomial dist, parentheses, and it's going to be 0, comma, 10, comma, 0.1, comma, false. Okay, and it's 34%, just a little bit less. So I'm going to do it for 2 also, except what I'm going to do now is, I'm going to do it for 2, 3, 4, 5, 6, 7, 8, and so on. So I'm going to do that by just simply putting a series of numbers in this column. Nine and 10. Okay, these are all the possible outcomes. I'm going to get rid of this middle column here. Hopefully that didn't change anything. Yeah, it's still working. Okay, so now since I use that identifier, that relative identifier for the number of successes and the number of trials, the likelihood doesn't change. False, I'm not changing. I'm going to copy this down and calculate the probabilities for every one of these outcomes. Okay, there's the probability for all of these outcomes. Look at the probability for getting 10 out of 10. It's basically 10 to the minus 10th, right? It's vanishingly small, which you would probably expect, right? Pretty unlikely, right? So what do you think this is going to add up to if I add them up? Right, it represents all of the possible outcomes. It's exhaustive. Sure enough, it adds up to 1. Okay, so now if I asked you, let's say that you're running a clinic and you usually get about three people walking in on any particular day. You say to yourself, gee, what's the probability that I'll get up to 3 people on any given day? Because that's the number of, test kits I might want to bring with me or something like that, or diagnostic tests I might want to bring with me. So what's the probability that you would get up to 3 people coming into this place? Well, probably you would get 3 is 5%. Probably you get 2 is 19%. Probably you get 1 and 34. So the probability that you would get up to 3 people is going to be the sum of all of these probabilities. 3, 2, 1, 0. Right? So 98.6. So what's the probability we get more than 3? 1 minus that, right? So I'm going to do that two ways. 1 minus this, right? The other way I could do it is just to say the sum of all the possibilities that I didn't include there. Same thing, right? See what I did there? I just took the total of the possibilities above 4. What's the probability that I would get, let's say, may say 2 or more? What's the probability of getting 2 or more? Equals the sum of 2 or more. Going to be the sum. What's the probability we would get more than 2? It's equal to the sum now of, we're not going to include 2, so it's going to be this sum instead, right? So now, what about that true and false? Well, the reason for that true and false is that false indicates that I don't want the result to be cumulative. So instead of saying false, if I say true, the result is cumulative. For instance, if I say, let's see, binomial dist, right? Probability, let's see, number of successes is, let's say, 2, comma, trials is 10, comma, probability is 0.5, comma, 0.1 rather, 0.1, comma, and I say true instead. Let's take a look at what happens. I get 0.34%. Well, what does that 34% mean? That's something wrong there. Hang on a second. 10C4. Let's see.
Should it be B4?
Yeah, no, yes, you're right. It's B4. I got carried away there. Went right to the percentage, B4. That's better, right? And what is that the sum of? If you look carefully, that's the sum of 2, 1, and 0. So if I say binomial dist, comma, 2, comma, 10, and so on, it'll give me the probability for 2, 1, or 0 as the outcomes. That's what that cumulative means if I say true. So it kind of saves you a step if you're dealing with a lot of different numbers here.
So it's
Okay.
almost below that number?
It includes that number.
That number
Okay.
and all those below.
Right, exactly. So now if I did it here, equal binomial dist, parentheses, and I said, well, 1, I'm going to use cumulative true. I put in 1 here, comma, let's see, trials is 10, comma, 0.1, comma, true. What's the expectation here? The expectation is going to be the probability for 1 or 0, right, cumulatively. And indeed, it's the sum of those two. Okay, I tell you what, why don't you try a couple of examples of that? If you go to Blackboard, I'm going to pull up a document that's on Blackboard now. And it is lab session sample A. Okay, using Excel. I'll give you a minute. I'll tell you what. Why don't you guys try number 2? And I'll give you a couple of minutes to get ahead of me. Okay, do you want me to blow that up so you can see it? You don't have to open it. Can you guys read that? Number 2. Number 2. Maybe we can even make it bigger. Now I'm going to run that real estate on the screen. Okay, study indicates 4% of American teenagers have tattoos. You randomly sample 30 teenagers. What's the likelihood exactly 3 have a tattoo? 3 or fewer have tattoos. 4 or more have tattoos. Okay, you guys online following this? Are some of you trying it? Oh, good. Okay, good. Exactly 3. 3 or fewer, or 4 or more. So what were the 3 conditions we had to satisfy to do this? 1, Had to be binomial. Like yes or no, tattoos or no tattoos. Number two, what was it? Right, had to be the same likelihood for every test, for every trial. Right. What was the third one? Had to be exhaustive. Right. That was the third one. Right. Am I wrong?
Exhaustive.
Yeah. In other words, had to be all the possibilities had to add up to. Had to be independent. That's it. Okay. Don't have to be exhaustive. Right. For instance, if we were, it doesn't have to be exhaustive, because if we were looking at hair color and we want to know the probability of being a redhead, right? It could be independent, could be uh, uh, same probability for every person we test, but there could be a lot of other different hair colors. So the whole population doesn't have to be redheads, either redhead or not. Well, no, it is exhaustive, redhead or not redhead, so it would be anyway. I guess by nature it's exhaustive. You can't avoid it. Okay, I'm presuming you got a little bit ahead of me, so I'm going to get started myself. See if I can't move this around so I can read it. Okay, equals, first one is equals binom dist, parentheses, and let's see, number that'll satisfy me is going to, number of successes satisfy me is going to be 3, comma, 30 trials, 30 people were sampled. The probability is 0.04, comma, and since I'm only interested in that exact outcome, exactly 3, I'm going to say false for cumulative. Oops. I put an extra period in there. Get rid of that period. And I got comma. There we go. That should work now. There we go. 86%. Well, now how about 3 or fewer? Okay, equals binom dist. Parentheses. Let's see. Number of successes is going to be 3, comma. Number of trials is 30, comma, 0.04, comma, except this time I'm going to say true. Right? I'm going to say true because I wanted to include 3, 2, 1, and 0, 3 or fewer. And that's 97% basically. Okay, last one. 4 or more will have tattoos. I'm going to save myself a step here. What I'm going to do is I'm going to say to myself, 4 or more will have tattoos. Well, gee, I just calculated what the probability of 3 or fewer, right? So 4 or more is just going to be equal to what? 1 minus 3 or fewer. And that probability, oops, I messed that up. Escape again, equals 1 minus 0.96. Okay, about 3%. Right? It could have done it the other way, yes.
So when we do this for homework or on the test, how many digits do you want us to round on the answer?
Why does everybody ask that every semester? Okay, so 4, let's talk about this. Is a big deal. Now, anybody EOHS majors in here, environmental majors in here? No, right? All EPI majors, I guess, right? In environmental science, it's a big deal, right? Because you're taking measurements and your instruments have a certain accuracy and a certain precision. Very big deal what you round to. In statistics, first of all, number one, before you don't round at all until you get to the very end, because we're going to be doing a lot of different operations. You may take a number, you may square it, you may find a cube root, you may be doing a lot of things to it. So if you take a number and you round it and then you square it, you multiply the error. Right? So don't round until you're all through with your calculations. And in environmental science, what I would usually tell you to do is you would round to the number of significant digits that your measurements were. So for instance, if I have a thermometer that measures temperature in degrees, but not tenths of a degree, like 74 degrees or something like that, or 75 degrees, when I got to my end of my calculations and my calculation came out to the average temperature was 76.79999. Well, my measurements were only accurate to 2 significant digits, so I would round to 2 significant digits, like 76 or something like that. If it was 74.1, that's 3 significant digits. I would round to 3 significant digits. So it takes a little bit. You can use your judgment on that, right? But don't over round, right? So in other words, you don't have to get crazy about it. But in most of the examples we give you, a decimal place or 2 is probably fine, except on a percentage. Then, use your judgment. If the answer is 0.012, I would just keep it 0.012. I wouldn't round it to 0.01. Okay, but the real way to do this is to understand what the measurements were, how well you understood those values to make a decision about what would be appropriate rounding to, right? So if you get a chance, if you want to, if you're reading a example we gave you or something like that, and you want to think like an environmental, like a physical scientist, right? A physicist or a environmental scientist or something like that, just examine it and say to yourself, well, this measurement, how many significant digits is this measurement that I'm starting with? And that's I don't want to start out with an instrument that only give me readings to 3 digits, and then give somebody an answer in a problem to 6 digits. Right? Doesn't make any sense, right? Because your original readings were not that accurate. Okay, makes sense. And you can always ask us again, which you will anyway, because everybody asks that all the time. Okay. You guys online, you get the same thing? Okay, good. All right, good. So I'm going to move on to the normal distribution. So I'm going to put this stuff away. Let me just make sure I don't leave anything out. If you open up the help function for the help for functions in Excel, it will show you this table. And you can actually type the values into this table if you're uncomfortable just, using little hints and so on. So I don't think, most of you probably won't need that. Make sure I didn't leave anything out. Oh yeah, there's one more thing I wanted to mention. We just mentioned that one way of looking at this, let me go back up here to our example that involved, I'm going to take our tattoos again. Remember that Galton machine we just looked at, where the outcomes for the number of right turns and left turns, basically where those balls landed at the bottom of that Galton machine, was basically the number of left turns and right turns. So if there were 20 layers of pins, then this would be 10 left turns and 10 right turns. This far end here would be 20 left turns out of and no right turns, and so on and so forth. This would be 20 right turns. Okay, so basically, since the probability was 0.5, we formed basically what approximates a normal distribution, right? With a mean of 10, the outcome being 10 balls that went to the right. Let's do the same thing now with this problem we just looked at with the tattoos. Okay, so first of all, if I take 30 people and I want to know what's the most likely outcome or the average outcome that I will have for the number of people out of 30 that are going to have tattoos, right? P is equal to 0.04. So what's my expected outcome there? It's N times P, right? So what's that going to be? It's going to be 0.04 times 30. It's going to be what, 1.2? Okay. So that's basically my mean. I'm going to have approximate a normal distribution where half the time my values are going to be below 1.2 and half the time they're going to be above 1.2. Okay, that's the value that I would expect to get. Now, how spread out is this distribution? Well, we need to know what the standard deviation is to know what the spread is. We're going to get into this more later on as we talk about the normal distribution, but I can calculate a standard deviation for this outcome by saying standard deviation is equal to the square root of N, which is the number of trials, times P, which is the probability, which is 0.04, times 1 minus p. Sometimes you see that written as q, but it's 1 minus t, which is 0.96. So if I have to find the square root of this whole thing. So we'll just work that out. Calculator up. Oh, you know, I got my pen on top of that thing, so it doesn't work. Okay, so all clear. So 30 times 0.04 times 0.96. Okay, which is 1.15. So my standard deviation is 0.15. This is not a great example because it's pinned so far against the left side. Did I say it was 0.15? 1.15. Right? This is not such a great example because it basically goes past that value 0. Right? So, but good night. So let me do it again for the coins. Okay? Because I won't get such a since it's such a low probability, what this distribution will really look like is something like this, you know, because I can't get below 0 here. Okay, let's do it again for the coins. I'll get a fresh piece of paper. Okay. Let's say n is equal to 50 trials like we were looking at before. The probability of heads and tails is 0.5. And so the average number of heads I would expect to get when I toss 50 coins, n times p, it's going to be 25 heads. Okay, so what's our standard deviation for this distribution? It's going to be the square root of n times p times 1 minus p, which is 50 times 0.5 times 0.5. Okay, which is 0.25 times 50. Come on. Yeah. 0.25 times 50. Right, 0.5 times 0.5 is 0.25. It's equal to 12.5. We're going to find the square root of that, which is 3.5. Okay, I'm over rounding a little bit here, but 3.5. Right, what does that mean? That means our distribution of outcomes, right? Half of the outcomes, if I would toss 50 coins, half the time I would get less than 25, half the time I would get more than 25, right? Now, you may have noticed before when we drew normal distributions that it wasn't very often, most of the time, you don't see many values that are more than 3 standard deviations away from the mean. Usually this, even though this is asymptotic, which means technically it never really reaches the x-axis, it kind of like spreads out a little bit. Okay, technically, realistically, we very rarely see it going more than 3 standard deviations away. So we would expect that most of the values here are going to be between. I'm going to multiply that by 3, and I'm going to multiply that by 3 and call it approximately 10. We would expect to see our values between 15 and 35. We would expect almost none of the time to get values below 15 or more than 35 because it would be such an unlikely outcome. That 10 to the minus 10 that we were looking at in that other example that we were working on. So what we can do here is that we can actually use this normal distribution instead of the other methods we were using to say to ourselves, well, what's the probability of getting fewer than, let's say, fewer than 18 heads? How would I do that? Well, 18 heads is, this is 25, and this is 15. 18 heads is over here. So the probability of getting 18 heads or fewer is going to be the area in distribution that's over here. This is all the possible outcomes, so it's 100% or 1. Okay, so this area would represent the likelihood of getting that extreme of value below 18. I could have done the same thing by using that formula. I could have done the same thing by using Excel. Now I'm doing it using the normal approximation. We're going to take a much deeper look at this as we look into real normal distributions as we move on from here. Okay, so let's do that. So I'm going to get rid of this.
So N times P is how you got the median?
The median, yeah, the mean, really the mean. The mean number of heads that I would expect, right? The most likely outcome in the mean. Okay, so let's see. So I'm going to open up this next